What if you could see beneath your farm's surface? Not with an X-ray, but with a detailed, color-coded map showing exactly where your soil is rich and where it's starving. What if this technology could slash your fertilizer costs, boost your yields, and protect the environment all at once? Welcome to the Fields of Innovation YouTube channel. Smart farming starts here. Discover the future of agriculture, where we share information about technology applied in agriculture. Today, we're digging deep into a technology that's revolutionizing how we understand the very foundation of farming. 3D soil nutrient mapping. Healthy soil is the lifeblood of agriculture. It's the foundation upon which all crop productivity is built, supplying the essential nutrients, water, and microbial life that plants need to thrive. Without fertile soil, no amount of advanced technology can sustain high yields. In fact, studies show that an astonishing 95% of our global food production depends directly on soil health. When our soils degrade, our ability to feed the world is put at risk. This makes soil management not just a farming issue, but a global food security issue. For decades, farmers have relied on traditional soil testing to understand their land. This conventional method typically involves collecting a few soil samples from different spots across a large field, sending them off to a laboratory, and then waiting days or even weeks for the results. While this has been the standard, it has significant limitations. The process is time-consuming, expensive, and, most importantly, it often fails to capture the true variability of nutrients across an entire farm. A farmer might receive a single, averaged-out nutrient reading for a vast area, a number that oversimplifies the complex reality that nutrients are almost never evenly distributed. This lack of precision often leads to inefficient practices, such as over-fertilizing in some zones while under-fertilizing in others, which harms both productivity and the environment. So, what is the solution? Enter 3D soil nutrient mapping. This groundbreaking technology creates a detailed, three-dimensional model of how essential nutrients like nitrogen, phosphorus, and potassium are distributed beneath the soil surface. It goes beyond a simple surface-level analysis to visualize exactly where these nutrients are concentrated and, more importantly, where deficiencies exist at different depths. This provides a far more complete picture of soil fertility. The key difference between this and older methods lies in that third dimension, depth. Traditional 2D soil maps only provide a flat, bird's-eye view of nutrient levels. They can tell you what's on the surface but offer no insight into what's happening deeper down, where a plant's roots actually grow. For example, a 2D map might show abundant nutrients at the surface, but a 3D map could reveal that these nutrients are scarce just a few inches below, right in the root zone. This depth perspective is absolutely critical for understanding a plant's true access to nourishment and for making truly informed management decisions. To create these intricate maps, a suite of advanced tools is employed. Multispectral sensors, often mounted on drones or satellites, scan large fields rapidly, capturing data that goes beyond what the human eye can see. In-field soil probes are used to take real-time measurements of soil properties. This massive amount of data is then fed into sophisticated artificial intelligence AI models. These AI systems are the brains of the operation, processing the scattered data points and transforming them into a detailed, continuous 3D nutrient map that provides unprecedented insight. The process of creating a 3D soil map begins in the field. Farmers collect a strategic set of physical soil samples, but they also deploy a range of in-field sensors to measure key soil properties like pH, organic matter content, moisture levels, and electrical conductivity. This modern approach gathers far more data points than traditional testing, resulting in a dataset that is not only more comprehensive but also significantly more accurate in representing the variability across the farm. Once this rich dataset is collected, Geographic Information Systems (GIS) and powerful AI algorithms take over. GIS technology is used to georeference all the data points, linking each measurement to a precise location in the field. The AI then integrates this sample data with other layers of information, such as high-resolution, satellite, or drone imagery. Machine learning models analyze these combined datasets to identify complex spatial patterns and predict nutrient levels in the areas between the physical sample points. This intelligent interpolation is what allows the technology to build a continuous, high-resolution 3D model of soil fertility across the entire farm, leaving no patch of land unanalyzed. The final output is where the magic truly happens. The system generates layered, color-coded maps that allow farmers to visualize nutrient concentrations at various depths. You can literally see a cross-section of your soil, observing where nitrogen is concentrated 10 centimeters below the surface versus 30 centimeters down. This visual clarity is a game-changer, moving farmers from educated guessing to data-driven precision. It empowers them to make highly targeted decisions about everything from fertilization to irrigation, ensuring that resources are applied exactly where and when they are needed most. The applications of this technology in precision agriculture are transformative. The most immediate and impactful application is matching fertilizer use to precise crop needs. Instead of the traditional practice of applying a uniform amount of fertilizer across an entire field, farmers can now use the 3D maps to implement variable rate application. This means crops in nutrient-rich zones receive less fertilizer, while those in deficient zones get a targeted boost. It has to move from a one-size-fits-all approach to a bespoke prescription for every square meter of the farm. By clearly identifying these nutrient-rich hotspots and nutrient-poor zones, farmers can strategically manage their fields to maximize crop growth while eliminating waste. This level of zoning ensures that no area of the farm is overlooked or mismanaged, leading to more uniform and robust crop performance. The economic and environmental benefits are profound. Targeted fertilizer application directly lowers input costs, one of the biggest expenses for any farming operation. At the same time, it significantly reduces the environmental impact by preventing excess nutrients from running off into rivers and leaching into groundwater. This helps combat water pollution, eutrophication, and the release of greenhouse gases like nitrous oxide, which is linked to nitrogen-based fertilizers. The benefits for both farmers and the environment are clear and compelling. First and foremost, farmers see a direct impact on their bottom line through lower input costs. By applying only the necessary amounts of fertilizer and water, they save a significant amount of money. This efficiency also leads to a healthier environment. The reduction in over-fertilization minimizes chemical runoff, preserving the delicate balance of local soil and water ecosystems for the long term. These smart practices directly translate to improved crop yield and quality. When plants receive a balanced and consistent supply of nutrients throughout their growth cycle, they become stronger, healthier, and more resilient. This results in not only higher yields but also higher quality harvests that can command better prices in the market. Perhaps most importantly, 3D soil mapping promotes long-term soil sustainability. By optimizing nutrient management and preventing the depletion of essential minerals, this technology helps ensure that the soil remains fertile and productive for future generations. Securing the legacy of the farm, 3D soil mapping doesn't operate in a vacuum. Its true power is unlocked when integrated with other smart farming technologies. Drones are used to capture high-resolution aerial data. Internet of Things (IoT) devices continuously monitor soil conditions in real time, and satellites provide a large-scale overview of crop health. When the data from these tools are combined, farmers gain a holistic, multi-layered view of their land that is more comprehensive than ever before. The insights become even more powerful when soil maps are linked with dynamic data streams like weather forecasts and crop growth models. By combining a 3D nutrient map with an upcoming weather forecast, a farmer can make smarter decisions. For example, an AI system could warn against applying fertilizer right before a heavy rainstorm, as the nutrients would likely wash away. Instead, it might suggest a better time for application to maximize absorption and minimize waste. This leads to the ultimate goal: AI-driven recommendations, such as the exact amount of fertilizer needed for a particular zone, a precise irrigation schedule, or even suggestions for crop rotations that will naturally improve soil nutrient dynamics over time. This isn't just theory. Real-world case studies demonstrate the measurable benefits of 3D soil mapping. In the United States, large-scale corn farms in the Midwest are using this technology to optimize their nitrogen application. The results are impressive, with some farms reporting a reduction in fertilizer use by as much as 20%, while maintaining or even increasing their yields. Across the Atlantic in Europe, prestigious vineyards in France are leveraging nutrient mapping to improve grape quality. By tailoring fertilization to very small, specific vineyard blocks, they can achieve the perfect balance of nutrients needed for premium winemaking. And in Asia, technologically advanced rice farms in Japan are integrating detailed soil nutrient maps with robotics to automate and optimize planting, irrigation, and fertilization with incredible precision. These examples from around the world consistently show the same positive outcomes: higher yields, reduced costs, and healthier, more sustainable soils. Of course, like any emerging technology, 3D soil mapping faces certain challenges and limitations. The high upfront cost of the necessary sensors, drones, and AI software can be a significant barrier to entry, particularly for smallholder farmers who may not have the capital for such an investment. Additionally, using this technology effectively requires a new set of skills. Farmers and their teams must be trained to operate the equipment, interpret the complex data, and apply the insights correctly in their day-to-day operations. Finally, issues of data accuracy and standardization remain. Differences in sampling methods, the quality of sensors, and the algorithms used by different AI platforms can sometimes lead to inconsistencies. Developing industry-wide standards will be crucial for ensuring the reliability and comparability of data across different systems. Looking to the future, the potential for 3D soil mapping is immense. As the technology becomes more refined, cheaper, and more accessible, it has the potential for global adoption. It could become a standard practice in regions around the world that are grappling with severe soil degradation and food insecurity. In the grand scheme of things, this technology will play a critical role in advancing sustainable agriculture, with the global population projected to grow dramatically in the coming decades. Precise and efficient soil management will be absolutely essential for feeding billions of people without further harming our planet. Furthermore, 3D mapping is poised to integrate with other forward-thinking practices like carbon farming and regenerative agriculture. By accurately monitoring changes in soil carbon levels, this technology could support climate-smart agricultural initiatives and even help farmers participate in emerging carbon credit markets. In summary, 3D soil nutrient mapping offers a powerful suite of benefits, including significant cost savings for farmers, enhanced environmental protection, higher crop yields, and the promotion of long-term soil sustainability. It is a true game-changer because, unlike traditional soil testing, it provides real-time, precise, and three-dimensional insights that empower farmers to make smarter, more effective decisions than ever before. It is a cornerstone of the future of agriculture. What are your thoughts on this incredible technology? Do you have any questions about how it works? Let us know in the comments below, and don't forget to share your own ideas on agricultural innovation. For more deep dives into the future of farming, make sure to subscribe to Fields of Innovation. Thank you for watching.